Hey guys, I'm gonna kind of walk through the first part of this chapter. Hopefully you watched the Edpuzzle and it cleared up a few of these ideas. I want to let you know this is in your books, chapter 18, and this really would start at 18.2. Your book goes into a lot more depth than we are going to go into. So I would focus more on this summary page that I gave you than trying to read the book unless you feel like it will be really helpful for you. So, flow of charge. So just like if you think about water, why would water flow from one area to another? Okay, so water would flow downhill, meaning some part of the water is higher and it can go lower. So this is the same idea with electricity. Electricity is a flow of charge. So why would the charge flow? Because it's higher in one spot and lower in another, so it will flow. And so that difference in charge from one place to another is the potential difference. Okay, and again, this is potential in reference to potential energy. Not that like there could potentially be a difference, but that there is a difference in the amount of potential energy, okay, within a current. So why would, the charge would flow? Because there's a difference in potential energy. It's going to flow towards the lower potential energy. But water will flow downhill until there's no further downhill to go, right? So when all of the water is down at the low spot, it'll stop flowing. When all of the charge has moved so that there's no difference in charge from one spot to another, it will stop. Okay, so when there is no potential energy, there is no longer a flow of charge. And so there would be no more current flowing through your system. So if we want to keep current flowing, we want to keep electricity moving, we have to keep a potential difference. We have to have things at a different potential energy throughout the circuit. I wanted to throw in here also, we have this unit of a volt. And that's what we kind of measured the potential difference in, is volts. And 1 volt is a difference in 1 joule of potential energy per 1 coulomb of charge. And remember, a coulomb is a way to measure charge because the charge on any individual proton or electron is so minuscule that we picked the charge that's, of a lot of electrons or a lot of protons, and we called that amount of charge a coulomb. So an increase in 1 volt is a change in 1 joule of potential energy per 1 coulomb of charged particles. Alright, so let's think again about current being similar, current of water versus a current of electricity. Okay, so current carrying wire has a net electric charge of 0. Okay, so if I was going to draw a wire here, not a very good one. So it's got protons all along the wire, nuclei of the atoms here. And around them all, they've got electrons. Okay, so when we say electricity is a flow of electrons, okay, it's not like this one is just going to jump over here. Okay, so basically this electron is going to go here, and they just kind of shuffle along from one atom to the next atom to the next atom to the next atom. Okay, so they just kind of move all together. But the whole wire itself has an equal number of protons and electrons. Okay, so the net charge is 0 because there's an equal number of positive and negatives here. But if there's something on this side pushing those electrons this way, maybe there's a positive charge over here. Okay, all these electrons, oops, that should be negative. Negative charge here, all these electrons are going to be pushed away It's kind of a domino effect, right? If this big negative charge here pushes this electron away, and then this electron moves to get away from that electron, boing, 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 boing. So anytime we're talking about the flow of charge, it's called an electric current. Okay, so usually most of the time we're talking about electrons kind of flowing down a wire or something like that. But if you think about in water, excuse me, or something like that, if you're in a fluid, okay, the whole atom can move. Okay, so if you have an ion, which is a charged particle that's bigger than an electron, it's like a whole atom, right? So I could have an entire charged particle move in the fluid. Okay, it's not really the same as electrons jumping from atom to atom to atom, but it's still in a charge that is moving, so it'd be considered electric current. When we're talking about current, we're talking about the movement of charge. Okay, and that is called ampere. So current is the flow. We measure the current, I'm going to wiggle through here, in amperes. Amperes is our unit that we measure the flow of charge with. Okay, so 1 ampere of current, 1 ampere of current is that we are moving 1 coulomb of charge per second of time. Okay, so an ampere or an amp, okay, is 1 coulomb of charge that is moving per second. All right, so then we have, where does this charge come from? Voltage sources. Okay, batteries and generators, whatever it is that is providing that potential difference is your voltage source. And we call it the electromotive force. But it's just a force that's kind of causing that difference to make the electrons or make the charged things move. Okay, and here's a big idea. Voltage causes current. Okay, so voltage is that difference in charge or difference in potential energy. And this is the movement of charge. So the idea is current is the movement. Why would they move at all if there was no difference? They wouldn't. Okay, so you have to have a difference in charge or a voltage first, potential difference, before the charge is going to move. Okay, so the difference in charge, the voltage, causes the movement of charge or the current. Okay. We're going to just do 34.4 and 34.5 here. So the resistance. So anytime you hear the word resistance, it's something kind of fighting back or something stopping something from happening. And that is exactly the same in electricity. So the resistance of a wire, how much it's going to try to stop the flow of electricity, depends on what the conductivity of the material, so what the metal's made of, right? Is it a copper wire? Is it an aluminum wire? Whatever. And how thick it is. And also how long it is. Okay. So let's think about this. Okay, so the amount of charge that flows depends on the voltage, which remember is the difference in charge, right? How much driving force is there? But it also depends on the resistance. How much is the material fighting that flow of electrons? How tightly is that material trying to stop the electrons from moving? There are some very, very few cases where that resistance becomes zero. Okay, meaning those electrons could flow and there's nothing fighting them. They can flow very, very easily, and that's called superconductivity. And it's not really encountered very much in the real world. But here we have another unit here. Okay, so we have resistance, and its unit is ohms. Okay, and ohms has this great symbol. I don't even remember what Greek letter it is, but it's one of these guys. Yes. All right, so Ohm's law says, okay, the current, and I wrote it up here, the current in a circuit is directly proportional to the voltage. Okay, so if the voltage got bigger on the top of a fraction, if the voltage increased, the current would increase, but inversely proportional to resistance. So resistance is on the bottom. If the bottom part of a fraction gets bigger, okay, the fraction that it is a part of would get smaller. So as resistance increases, current decreases. You can always just kind of use this formula here. And we can again kind of think about units. So current is measured in amps. Current. Volts is voltage. And ohms is resistance. Okay, so hopefully you have also this page fairly handy. I think I want to do again where I kind of do a handful of these, and then I'm going to ask you to kind of go back and do the rest. Okay, so electric current. And I love, try your best to use the analogy of water flowing in a current and electricity flowing in a current, and it'll hopefully help make more sense here. It says water doesn't flow in the pipe when, so if this is a pipe, and this guy, you can kind of see there's this little water level here. So it's a curved pipe and there's water in it. If he was holding it, I'm going to turn my paper a little crooked here, perfectly sideways. Okay, would the water flow? I hope you know the answer is no, right? Water only flows downhill. So if it's level, it's got nowhere to flow. Okay, but as soon as he starts to tilt it, then the water is going to flow and come out this end. And so he's got the flow of water, a current of water, because his two ends are at different levels. Okay, so another way of saying this is that water will not flow in the pipe when both ends have the same potential energy. In this case, it would be gravitational potential energy, right? The higher something is, the greater its gravitational potential energy. But tip the water pipe and increase the potential energy of one side, so there is a difference in potential energy across the ends of the pipe, as in B, and the water will flow. Similarly, increase the electric potential of one end of an electric conductor, so there's a potential difference across the ends, and charge will flow. So imagine here this guy has this perfectly flat. I know that it's weird that it's supposed to be flat, but if your paper is straight, it's not really flat. But imagine it's flat. And he takes this pipe and he raises the potential energy of both sides. Okay, so now the pipe would be up here. Okay, is the water going to flow now? Okay, we raise the potential energy. Will it flow? No, it will not. Okay, because from one end to the other, they have the same potential energy. The key idea here, I underlined it, is there has to be a difference. Okay, if I raise both ends, then they're both higher. There's not a difference between them. So you kind of got to think about that a little bit. All right. So I'm going to do A and B. I'm going to ask you to do C and D here. So the unit of electric potential difference. So the difference in potential energy is measured in volts. That's our unit. And when we're talking about, well, what do volts measure? They measure voltage. It's kind of weird. Okay, so a volt is a measure of voltage. We just basically took what we said over here and put it in our little cartoon. All right, so I'm going to skip those two, try to do that one, and figure out that blank. Okay, 2, complete the statements. A current of 1 ampere of flow is a flow of the charge at the rate of, well, if I look back at what I wrote a little bit ago, I said 1 ampere is 1 coulomb per second, or 1 coulomb per 1 second. So 1 ampere would mean 1 coulomb per second. So use that logic for B. C, 1 volt is the potential difference between 2 points if 1 joule is energy needed to move. And again, I think to myself, well, what did I write down? I said 1 volt is 1 joule of energy per coulomb of charge. So if I have 1 joule of energy, I am moving, it's the energy needed to move 1 coulomb of charge. 1 and a 1 and a 1. All right. And last one here. Which offers more resistance to water flow? A wide pipe or a narrow pipe? Or think about if I had a straw or something. I don't know, whatever. If you're trying to pour water out a downspout or a gutter, you know, would you rather have a wide pipe or a narrow pipe if you want the water to be able to flow through easily? Okay, so if we're talking about flowing easily, I'm going to pick the wide pipe, right? So the opposite question is kind of what's asked here. Which would have more resistance? Which would kind of slow the water down more? And so that would be the narrow one. Okay, there's your clue for this the last blank on that one. All right, backside, we're using some math. So if you don't have your calculator, I would hope you would please pause it and go get your calculator. So here's our equation. Current equals voltage divided by resistance. Remember, current is in amps or amperes. So that's the unit that would plug in there. And voltage is in volts divided by resistance is in ohms. Okay. Alright, so how much current flows through a 1000 ohm resistor when 1.5 volts are impressed across it? So I look at my equation, I say, okay, I'm given an ohm and a volts, which means I don't know the current. So I go C for current equals 1.5 volts divided by 1000 ohms. 1.5 divided by 1,000, I sure don't know what that is, 0.0015, and I found the current, so my unit should be amperes or amps. Okay, I'm going to skip to 3 here. The resistance of the side lights on an automobile are 10 ohms. How much current flows in them when they're connected to 12 volts. So again, I'm given ohms, I'm given resistance, so that's going to go on the bottom, and I'm given volts or voltage, so that's going to go on the top. So I have current I don't know equals 12 volts divided by 10 ohms, and I go 12 divided by 10, 1.2 amps. Alright. 5, we're just going to do A together. During a lie detector test, a voltage of 6 volts is impressed across 2 fingers. When a certain question is asked, the resistance between the fingers drops from 400,000 ohms to 200,000 ohms. What is the current, A, initially through the fingers, and B, when the resistance between them drops? Okay, so it doesn't say anything about the voltage changing, right? So I'm going to say the voltage is always 6 volts, and initially my resistance was 400,000 ohms, and I'm finding the current here. So I have 6 divided by 400,000. It's a pretty small amount of current, which makes sense. We're not trying to electrocute somebody when we give them a lie detector test, so we wouldn't want to pass too much current through them. Alright, so I'll have you do B. I'll go ahead and do 6. So how much resistance, so this time it says how much resistance, so resistance is what we don't know, allows an impressed voltage of 6 volts to produce a current of 0.006 amps. So current is on the left side of the equal sign, that's in amps. So that's going to go over there. I have a 6 volt voltage source, and resistance is what I don't know. Remember, when your unknown is on the bottom all by itself, we have that wonderful trick where it can just trade places with the opposite side there. So I'm going to go 6 divided by 0.006, and I would have 1,000 ohms of resistance. Okay, so basically this much resistance is going to slow down the 6 volts of electricity enough that only 0.006 amps of flow can happen. All right, 8. What is the voltage across a 100 ohm circuit element that draws a current of 1 amp? So again, I've got to know the amperes, know the current, equals what is the voltage. So this time I do not know the voltage, but I know 100 ohms of resistance. Okay, so my unknown is divided by 100, so I'm going to multiply by 100. So 100 times 1, 100 volts. The weird thing is this is V for voltage, this is V for volts. Doesn't really matter. All right, last one. The current in an incandescent lamp is 0.5 amps when connected to a 120 volt circuit, and 0.2 amps when connected to a 10 volt source. Does the resistance of the lamp change in these cases? So I'm going to do the first one. So I know to start, the current is 0.5 and the voltage is 120 volts. Okay, so remember my unknown's on the bottom all by itself, so I'll trade places there. So to start, 120 divided by 0.5, the resistance is 240 ohms. Okay, so you need to do that same kind of math with the second part and be able to try to answer this question. Does the resistance change? Okay, so you're going to have another math setup and then a yes or no and why your answer is what it is. As always, let me know if you have any questions. Later.